Swayam Prabha. Digital India. Educated India.
All right, now let's go to tail sub problem 2. Of length 2. So now we are moving to time instant n minus 2. Okay. So now assume once again we are at time, assume we are at time n minus 2, right, and assume also that assume the stock inventory level is x n minus 2. Okay, we are, suppose that is the nominal level we are at, right. Now what should the inventory manager do now at time instant n minus 2? Now at time instant n minus 2, he whatever decision he takes will incur him a cost for that particular period. All right. So suppose he is at he takes a decision to order some goods, he will incur the cost of ordering, ordering, under ordering or over ordering, and or whatever, all of that cost for that particular time period is incurred. But then that decision also will impact the state that will occur in the future. The state that will occur in the future is denoted x n is going to be x n minus 1. Right. Now, x n minus 1 will get realized as a function of x n minus 2, x u n minus 2 and the noise w n minus 2. So, x n minus 1 will come about through that. But the previous calculation that we have done has told us what the optimal cost would be if you were to reach any such state x n minus 1. So, as a function of the state that you would reach, we have already, as a function of the state that you could potentially reach, we have already computed the optimal cost, right. We already know that if I were to reach a certain inventory level in the next day, what the optimal cost is going to be. So, the way the inventory manager can think is, he has to now minimize two things. One is he has the cost that he will incur in this period, and the cost that he is going to incur if he reaches a particular state. So, effectively the value function j n minus 1 that we have calculated for state n minus 1 onwards becomes the terminal cost, okay, becomes the terminal cost for this particular stage, for stage n minus for doing the calculations at stage n minus 2. So, n minus 2 at n minus 2, it is almost as if you have one stage to go with when you incur a cost at this particular period, and there is going to be a terminal cost based which is given to you through your value function j n minus 1 as a function of the state that you would end up in, right. So, the inventory manager, the optimal inventory to order is inventory to order minimizes So, it minimizes expected cost in period n minus 2 plus the expected cost in n minus 1, assuming an optimal policy is used in n minus 1. Okay. So, the expected cost in period n minus 1, assuming an optimal policy is used in that period n minus 1, right. So, what does this equal? This equals your R of expectation of these terms, R of x n minus 2 plus C of u n minus 2 plus, now if you were to reach some state x n minus 1, what would be the optimal cost that you would incur? Well, the optimal cost you would incur is something you just calculated, is j n minus 1 x n minus 1. So, this is why doing this, you can see this is why the doing this calculation in the previous step for every possible value of x n minus 1 is useful. So, it is useful to do this for every x n minus 1, because now we have the value function, or the you know what, now we have what the optimal cost is starting from any possible initial state. So, we can plug this in as a function of that state, right, and now that state can get realized through x n minus 1 and u n minus 1, and then we can calculate the expectation and so on, but we can plug that in as a function over there. And so, as a result, we can we know we can talk of what is going to be the optimal cost at this particular at stage n minus 2, all right. So, now remember x n minus 1 is x n minus 2 plus u n minus 2 minus w n minus 2. So, because of this, now we have that the last term becomes this can be substituted in the last term. Once again, as before, x n minus 2 is deterministic, u n minus 2, because it is a function of just x n minus 2, is also deterministic, right. So, consequently, this our minimization now becomes is a minimization over u n minus can be written in this way. So, you can do x n minus 2 plus minimizing this over minus 2 C of u n minus 2 plus expectation now of j n minus I am running out of space here, j n minus 1 of x n minus 2 plus u n minus 2 minus w n minus 2. This whole thing is denoted, can be denoted as j n minus 2 of x n minus 2. Let me write this more neatly. So, this here is a function of x n minus 2, write this as j n minus 2 of x n minus 2, and the process of calculating this, as before, like I mentioned, the minimization here, this also yields us u n minus 2 star as a function mu n minus 2 star of x n minus 2. So, all the noise here is in w n minus 2. So, the expectation is with respect to w n minus 2. So, as you can see, once again what we have got is, by through this substitution, now we have got the policy at time step n minus 2, all right. So, more generally what we are doing is, what we are getting is this particular recursion, that the value function at time k as a function of this, as a function of a nominal state, not necessarily the realized state, okay, as a function of a nominal state x k is going to be r of x k plus the minimization over u k greater than equal to 0 of c of u k plus expectation of, plus the expectation of the value function from the next time onwards, evaluated at that state which is realized in this way. Okay. Now, this equation actually is essentially the cornerstone of solving such problems. This is what is called the dynamic programming equation. Dynamic programming equation for the inventory management problem, for the inventory control. So, this is the dynamic programming equation for the inventory control problem. So, these functions these functions j k, as I have mentioned, they are denoted, they are called the value functions. They are effectively capturing for you the optimal cost for the tail sub problem that starts from time k, starting from any instant, starting from any state x k at that time instant k. So, effectively what the problem has done is, what you were looking for is the optimal cost starting at time 0 for your specific initial state x 0, what this way of solving has effectively done is solve for you not just the optimal cost for that particular time and that particular initial state, but also for every intermediate time and every intermediate initial state. But this may seem like it is it may seem wasteful, because you have solved, you have effectively tried to solve so many other additional problems in order to solve one. But it turns out that that is the source of the simplification, that if you do this step by step, you would be in the way that is illustrated here. Okay. You would actually get the solution for the original problem, right. So, the way one proceeds is that you start from the last step, solve that particular problem, go one step back, solve that problem, substituting the value function from the last step in it, then go to step n minus 3, substitute it in it the value function of step n minus 2, and so on and so forth, and eventually you come to step 0, where you would get, which is in fact essentially your original problem. The major simplification that has happened is that at every stage, the optimization that you are doing is now not over the space of functions, you are optimizing only over the space of actions, you are optimizing over vectors rather than over functions. That is where the major simplification has come, and all these other benefits that we have got, which is namely that we have got the value function and etc. along the way, they are just side benefits of making this particular simplification. That is not what we aimed for. What we aimed for was the collapse of complexity from having to minimize over that many 5 raised to 10 times 5 raised to 10 times 5 raised to 10 many options, to something much more concrete, which is just an optimization at each step, vector optimization at each step, all right. So, this is basically tells me puts us in a position to state the dynamic programming theorem, Okay. So it says that for every initial state, so okay, I should mention the problem that we are looking at. We are looking, so suppose we are, so to state the dynamic programming theorem, suppose we have, you are minimizing this objective, which is minimize this subject to plus and xk plus. So the dynamics are that xk plus 1 is fk of xk uk wk, and you want to minimize this over all policies pi given by mu 0 to mu n minus 1. Okay. Right. So the theorem is as follows, and the initial state, let us say, is x 0. I will mention that as part of the theorem. So for every initial state x 0, the optimal cost j star of x 0 of the above problem is equal to j 0 of x 0. What is j 0 of x 0? It is given by the last step of the following algorithm. Okay. So the Jn of xn is simply Gn of xn. So you just initialize the value function at for simplicity, just initialize Jn of xn as Gn of xn, and then write this the value function at each step k before that in the as follows. You minimize this uk, where the minimization is with constraints uk of xk, expectation with this of, now this is the cost in that time period, which is gk of xk uk comma wk plus jk plus 1 now, but then you need to substitute xk plus 1 through using your dynamics, using these dynamics here. Okay. So fk of xk uk wk, and you do this for k equal to 0 all the way till k n minus equal to n minus 1. In other words, actually you need to do this in reverse. You start from k equal to n minus 1 and proceed all the way till 0, right. Okay. And moreover, if you write uk star equals mu k star of xk minimizes, so let's denote this by star, minimizes star, then mu 0 star till mu n minus 1 star which is denoted by pi star is optimal. So, this policy is actually optimal. Alright. So, this boxed thing here, equation star, is called the dynamic programming equation. Dynamic programming equation. It was discovered by by a scientist called Bellman. So, it is often also called the Bellman equation or the Bellman optimality equation. Okay. This is called the Bellman equation. So, this is what we so this is going to be the way of solving any dynamic programming problem. Essentially, you start from the last step as if you had a time horizon 1 problem, find the optimal thing that you would do in that problem, use the cost that the optimal cost or the value function that you get from that problem as the terminal cost of that problem with one step before. Then find the solution of the problem with one step before, find the value function for that, and then move one more step behind, and so on and so forth, and coming all the way back. Then you eventually get to time step 0 and a terminal cost, which is essentially the value function from for time step 1, and that is how you get to the optimal solution of your problem, of the dynamic programming problem. Okay. So, effective let us just once dwell on what enabled this. The thing that has enabled this is that our optimal cost, if you see our optimal or rather the cost function, if you see, is actually additive. You see, it is a function of you have your terminal cost and you have these costs at each step, right. You have costs at each step, plus your state equation is also in this form, where the next state is determined by the previous state, the action you take in that previous state, and the noise at that time. It does not depend on in more complicated ways on steps on states before or states after, and so on. So, this structure of a separable cost function and also of this kind of interrelation between the current state and the next state, that is what allows us to make this work. This is what makes this kind of a cost which is cumulative cumulative of the costs over at each time step. This sort of cost occurs when you are, say, computing, say, the total cost, total amount of money you make over a time horizon, or say the total amount of distance you have to travel, or the total amount of time spent, etc. Any of these things which are additive across time periods can be written in this sort of form, and that's once it is additive like this, it can be reasoned through in a recursive manner, and that's precisely what's being done, what we are doing here. So, that's what we get to. This is what's called the dynamic programming equation. So, now only one special topic remains here, which is solving such problems when you are dealing with when you have problems with a very specific cost structure, and that's what I will do next. We will talk about problems where the cost function is quadratic and the dynamics are linear. In that case, a very simple form emerges for the optimal policy. Okay. So, the optimal policy and the optimal cost function ends up having an extremely simple form, and that's what I want to just show you. So, we let us now apply what we know about dynamic programming to a problem with a very specific structure, where the cost is quadratic, the dynamics are linear, and the noise is independent across time instants. Okay. This is a favorite problem of control theorists and in operations research. It's what's called the problem of linear systems with quadratic cost. And we will find what the optimal policy for that sort of problem is. Now, the recall before I go into this specific problem, recall what we were talking about in the for this in the previous lecture, which is we were referring to a problem where you wanted to minimize a cost like this over a time horizon n, a cost that is comprised of a terminal cost and a cost at each step, and we had dynamics that were given in this way, which were in which the next state was defined as a function of the previous state, the actions and some noise.